Hello, everybody. I am Vladimir Koltsov from Khlopin Radium Institute, St. Petersburg, Russia. My presentation is about the width of gamma line and the photon structure. The basis for additional consideration of the question about the natural width of the emission of line of gamma quanta or photons in the decay of excited states of nuclei is as follows. The suppression of low energy electromagnetic transitions in nuclei inside metals was recently discovered. This occurs due to the suppression in metals of zero-point fluctuations of electromagnetic field which are resonant to the transitions and which stimulate the spontaneous emission of photons. I have to remind that zero-point fluctuations are inherent in all quantum systems, and even if there are no particles or photons in space, zero-point fluctuations remains there. I will mainly talk about emission of gamma quanta of photons by atomic nuclei, but all conclusions can be applied to emission of photons by atoms. The natural energy width delta E of the emission gamma line is the smaller, the larger the half-life of the excited state. So, the width of gamma lines for emitting nuclei in metals should decrease along with the rate of their decay. A gamma line width can be measured in mass-Bauer experiments by the shape of the absorption line of gamma quanta, depending on the relative speed of the emitter and the absorber. The outline of the presentation is as follows. At first, general points about the natural line width delta omega of photon or gamma radiation. Then I will talk about reasons for the appearance of the width of the gamma line in mass-Bauer experiments. It will be shown here that the width of the gamma line is determined not only by the half-life of the emitting state of the nucleus, but also depends on its age and the time of radiation of the absorbing nucleus. Then, to explain the properties of gamma line width, I will formulate a hypothesis about the structure of a photon, which includes a new type of electromagnetic wave that does not have energy, abbreviated as zero wave, and an energy quantum on the tail of this zero wave. This hypothesis is the central point of the work. Then I will talk about some consequences of this hypothesis, and finally I will talk about the possibility of detecting zero waves and prospects for their practical application. The full text of this presentation in my 2022 paper, the full reference to the paper, is the end of the presentation. So, I start with a reminder that today the definition of gamma quantum photon is obtained from the procedure of second quantization of electromagnetic field in quantum electrodynamics. A photon is a sinusoidal wave of electromagnetic field with a frequency omega 0 that is infinite in time and is a solution of Maxwell's equations in free space. Just to such an infinite wave of energy of the gamma quantum, h omega 0 is corresponding. In reality, nuclei don't emit monochromatic photons. The radiation process has a finite duration in time, and photons have a distribution in energy delta E, which corresponds to the width in the radiation frequency distribution delta omega. The width delta omega can be measured in mass-Bauer experiments. A feature of mass-Bauer experiments is that one nucleus emits a photon the other nucleus absorbs the photon. And it is not obvious who creates the gamma width, the emitter or the absorber or both. The general relationship between the spectral width delta omega and the duration of radiation delta T radiation is seen from the Fourier transform of the wave fragment of electromagnetic field strength. The spectral distribution of photons intensity is determined by the duration delta T radiation of electromagnetic wave train. In classical electrodynamics, for sinusoidal oscillations of an electric charge with a damped amplitude x during time delta T radiation, the amplitude epsilon of the intensity of the radiated electromagnetic field also decreases with time. The spectral intensity of radiation depends in a complex way on delta T radiation, but in general terms, the spectral intensity can be approximated by this simple formula. The spectral width delta omega is determined by the decay time of the oscillation amplitude and radiation duration. In quantum mechanics based on the non-relativistic perturbation theory, which initially included the exponential decay of the radiating state, Weizsäcker and Wigner obtained the spectral distribution of photons emitted in the decay of the excited state. This distribution is the same to that was obtained in classical electrodynamics, but now in the expression for line width delta omega, the lifetime delta Th of the emitting level appears. The age of the level from the moment of the level formation to the moment of its decay. The width of gamma line should depend on the age of the emitting level. This dependence was studied in Mesbauer experiments with iron 57 nuclei for the emission of resonant gamma quantum of 14K. Here is energy levels scheme of iron 57 nucleus forming in cobalt 57 decay. The moment of population of the emitting level 14 cap can be measured from the accompanying gamma quantum 122 cap. It is a start signal in time. The moment of the transition from 14 cap level can be fixed by the time of detection of gamma quantum 14 cap. It is stop signal in time. So, it is possible to measure the age, delta T age, of the emitting level for a particular 14 cap photon. Already, in early Mesbauer experiments with iron 57 isomer, a decrease in the gamma line width with increasing age of the emitting level was observed by this way. Here is shown the schematic diagram of the fast-slow coincident system used in the two-dimensional Mesbauer spectrometer. But due to lack of time, I have to omit experimental details and go straight to the results. This figure shows the late coincidence Mesbauer spectrum using a source of cobalt 57 and copper metal. The time range for the age of the emitting level is indicated on the spectrum, and as the age of the emitting level increases, the width of the gamma line decreases. It is also seen from this figure. This result corresponds to conclusions of quantum electrodynamics when the interaction of charged particles is described by perturbation theory. The Hamiltonian of particles and electromagnetic field is divided into the Hamiltonian of free particles and free field and the interaction energy operator between them. In absence of photons, free electromagnetic field is consist of zero-point fluctuations. Then it turns out that the spontaneous emission of a photon by a system of particles is stimulated by zero-point fluctuations of the electromagnetic field. The matrix element of spontaneous emission of a photon of frequency omega 0 depends on the time of radiation of excited nucleus by zero-point field fluctuations, and that is equal to the h delta t h of the emitter level. Delta t h is equal to 0 at the moment of emitting level formation. This matrix elements leads to the following dependence of the emitted photon intensity on their frequency and the h delta t h of the emitting level. The width delta omega of the gamma line should decrease with the h of the excited level. The narrowing of the gamma line with the h of emitting level cannot be associated with only with a decrease in the width of this level. This was shown by the experiment with the tantalum 181 isomer carried out by Vladimir and his colleagues in 1983. Here is the energy levels scheme of tantalum forming in tungsten decay. When the absorber was shedded, from the emitter by a rotating shutter that opened the mutual visibility for a time of about 1 microsecond, a broadening of the 6 keV gamma line occurred by 6 times. From this Vladimir experiment, it turns out that the width of the gamma line is determined not only by the emitter, but also by the absorber, which, as it were, is tuned to the resonant absorption of the gamma quantum by the currently unknown radiation. This radiation precedes the emission of the photon energy. In quantum electrodynamics, the absorption of photon is described by the same matrix elements as the emission of a photon. The spectral width of the absorption line is given by this expression, which includes a time of radiation of the absorber nucleus. Now I can give general view of the gamma line widths in Mesbauer experiments. At first, as the age of the emitting level increases without using a shutter, the width delta omega of gamma line decreases. The Vladimir experiment showed an increase in the width delta omega when using a shutter between the emitter and the absorber, which opens the emitter only for a short time, delta T radiate. This means that when a photon is absorbed, some wave radiates the absorber nucleus before it absorbs the photon energy, and it is difficult to understand with the framework of existing concepts. Especially if we take into account that the half-life of the emitting state significantly exceeds the time of photon energy emission which is less than the duration of the gamma signal in the detector. Then we have to assume the following scheme of photon emission, which I will explain using an example of Vladimir experiment. Immediately after the formation of an excited state, the nucleus begins to emit an empty electromagnetic wave that does not carry energy, abbreviated as zero wave. The duration delta Th of this zero wave, together with the decay constant of the radiating level, determines the spectral width of the radiation. The energy quantum H omega is emitted at the end of this zero wave during short time delta T H omega. The absorber nucleus is irradiated with this zero wave, and the spectral distribution of resonantly absorbed photons depends on the decay constant of the excited level and the duration of irradiation of the absorber nucleus. From this point of view, Vladimir experiment scheme is as follows. After the formation of the radiating level, the nucleus immediately begins to radiate a zero wave of frequency omega 0. Delta T radiation is the part of this zero wave, the wave train that the absorber can see through the open shutter. The energy quantum is emitted on the tail of this zero wave during a short time delta T H omega. Delta T shutter is the emission part of this zero wave. It is cut off by the shutter and the absorber doesn't see it. Some properties of zero waves. A train of zero waves is emitted all the time after the formation of an excited state. It can be assumed that zero waves propagate at the speed of light. Then, for example, for the emission of the Mesbah isomer silver 107 with a half-life of 44 seconds, the train length is about 10 to 9 power meters. The question arises about the nature of zero waves. In terms of reflection and interference, the properties of zero waves are apparently the same as those of known electromagnetic waves. For example, these zero waves are not transmitted by the shutter in the Vladimir experiment. But these are not ordinary electromagnetic waves since they don't carry energy. This photon structure helps to understand the photon-wave particle duality. The zero wave is responsible for wave properties of the photon. The energy quantum interacts with matter as a particle. The zero wave with an energy quantum H omega on its tail resembles a pilot wave introduced by de Broglie to explain the wave-particle duality of electrons. An important subject is the stimulated emission of photon by an atom or an atomic nucleus, where one photon stimulates the emission of another photon. The emission of photons is stimulated precisely by quanta of photon energy, but not by zero waves. This is evident, for example, from the possibility of obtaining laser pulses of stimulated emission with a duration much shorter than the lifetime of excited states of atoms. Special localization of photon energy quanta explains Poisson statistics of spontaneous photon emission. Spontaneous emission of photons of frequency omega 0 is stimulated by resonant zero-point fluctuations of electromagnetic field, abbreviated here as ZPFs. Let us assume that the structure of zero-point fluctuations is the same as that for photons. The finite line width of spontaneous emission shows that the stimulation of emission is caused by zero-point fluctuations of various frequencies. Phases of zero-point fluctuations are completely uncertain in accordance with the quantum electrodynamics uncertainty relation for the phase of photons and their number. Then, for individual nuclei, the moments t and t stroke of stimulation of photon emission by zero-point fluctuations quanta with frequencies close to the resonant one, these moments are random in time. This gives Poisson statistics for the spontaneous decay of excited states. A possible source of zero wave is virtual transitions from the excited level to the ground state of the nucleus and back before the emission of an energy quantum. With this assumption, it would be possible to understand what the frequency omega of which process appears in the formula for the transition energy delta E is equal to h omega. According to quantum mechanics, energy fluctuation by delta E in virtual transitions is possible for a time delta T of modern of h divided by delta E. Accordingly, the frequency of virtual transitions will be of order of delta E divided by h. The width of the absorption gamma line depends on the time that the atom sees the zero wave before absorbing the energy quantum. How does the zero wave tune an atom to absorption resonance? Perhaps the zero wave in the absorber atom stimulates virtual transitions from the ground state to the excited state and back. The atom virtual being in an excited state before absorbing a quantum of energy somehow shapes the space of the atom and makes narrow the energy level corresponding to the excited state of the atom. After all, in the end, the excited state of an atom with its energy, which is one of the stationary solutions of the Schrödinger equation, is realized only when the atom finds itself in the state. And if we don't talk about zero waves, then before the absorption of energy quantum, the atom is not in an excited state. Therefore, the energy of the excited state is not determined before the quantum transition. It would be interesting to find a way to detect zero waves and study their properties in more details. For example, study the possibility of modulating the gamma line width due to additional irradiation of the absorber by resonant zero waves modulated by an oscillating shutter. The expected result of such experiment with ferrum 57 source is as follows: 14 gamma line width modulation with shutter modulation frequency. It is possible to create zero-wave generator without energy emission. After the formation of the radiating state, the zero wave will begin to be emitted. But the energy quantum itself may not be emitted if the decay occurs through some other channel. Then the zero wave will exist on its own without an energy quantum. Example of a zero-wave generator using a stack effect is shown here. When an electric field epsilon is turned on in a system of two degenerate levels, the upper level is populated if the stack splitting energy delta E is comparable to the temperature of the medium. After the levels split, the zero wave will begin to be emitted. And if the electric field is turned off before the quantum transition down, then the zero wave will be emitted without an energy, without the energy quantum. Perhaps zero waves can be used in practice. It is interesting to study the possibility of transmitting information using zero waves. And by detecting a zero wave, one can detect an excited object and predict its future decay. Here are references to the papers which I used in my presentation. Thank you for your attention. Bye.